Hello everyone, this is Madhuri, working as Assistant Professor in the Department of Electrical and Electronics Engineering at MLR Institute of Technology. Today I am going to discuss the topic armature reaction as a part of DC machines course. So by the end of this lecture, you will be able to understand what are cross-magnetizing effect, what is demagnetizing effect, and what is armature reaction. We'll be seeing in detail. So coming to armature reaction, we know that we have conductors in the armature and we also have field windings which are wound on the poles of DC generator or a DC machine. So the current which is flowing in the armature conductors, we know that it creates a magnetic field which is called as armature flux. This armature flux distorts and weakens the main magnetic flux which is produced by the main poles. So this effect of distortion of armature flux having effect on the main field flux is known as armature reaction. So basically this armature reaction has two kinds of effect. One is demagnetizing effect and the other is cross-magnetizing effect. So demagnetizing effect, this effect causes the reduction of the generated EMF in the DC generator, and this cross-magnetizing effect causes the sparking at the brushes. So we can see that the effect of armature flux, that is the flux which is generated by the current flowing in the armature conductors on the main field flux, is called as armature reaction. So it basically has two effects. One is demagnetizing effect, the other is a cross-magnetizing effect. This demagnetizing effect will make the generated EMF to be reduced and the cross-magnetizing effect will cause the sparking at the brushes. So to avoid how to analyze or how to in detail how these effects occur in the case of generator and how does the armature reaction occur in the DC generator will be analyzed in the further slides. So moving on to the case 1, consider we have a 2-pole generator which is on no load. So we are not loading the generator initially. So we are considering the generator which has 2 poles and it is under no load condition. So under no load condition, what happens when there is no load connected to the armature terminals? The current in the armature will be 0. So this is the first point. The current in the armature will be 0 under no load conditions. So under these conditions, there is only main flux or the main field flux. So this main flux is generated by the poles in the stator, that is the poles which are attached to the stator. So which are produced by the main poles. So this main flux is distributed symmetrically with respect to polar axis. So what is polar axis? Polar axis is the axis which is the center line of the field poles. If we consider this as north pole and this is the south pole, the line which is joining the 2 poles and which is passing through the center of the 2 poles is called as polar axis. So under this condition, under no load condition, the main flux which is generated in the main field poles is symmetrically distributed from north pole to south pole or along the polar axis. So this is now your polar axis. It is the axis which is passing through the center of 2 main field poles. So next, coming to the magnetic neutral axis, we can see that magnetic neutral axis is the axis which is perpendicular to the polar axis. So we can see this is nothing but our MNA, magnetic neutral axis. In this particular case, under no load condition, we have geometrical neutral axis also coinciding with the magnetic neutral axis. So magnetic neutral axis is the axis which shows the direction of induced EMF or the EMF generated in the generator. So it is the axis which shows the generated EMF, and we can see that geometrical neutral axis is the axis which is always perpendicular to the polar axis. So under no load condition, we can see that the MNA and GNA coincide with each other. So this is polar axis And we can see our MNA and GNA are perpendicular to the polar axis. So we can see that the brushes are always placed in the direction of MNA or on the MNA axis, so that we know that the axis of this MNA is also called as axis of commutation. Why? Because brushes are the place where the current from the internal circuit is carried away to the external circuit. These brushes carry the current from the internal circuit to the external circuit. So before these brushes carrying it to the external circuit, the current reversal happens along the MNA. So that is why this MNA is also called as axis of commutation. As we all know that the function of commutator in a DC machine is nothing but it converts the alternating quantities to the direct quantities. So MNA is the axis along which the commutation process is seen. So that's why we can call that MNA is also called as axis of commutation, as the brushes are lying on the MNA and these brushes are attached to the commutator. So that's why we can call this axis as the axis of commutation. Moving on to case 2. So now we consider there is current flowing in the armature conductors and there is no current in the field coils. So we have current in the armature conductors and the field current which is flowing in the field coils is equals to 0. So in this particular case, what happens is the direction of the flux produced by the current in the armature is maybe determined by corkscrew rule. So if we consider a screw, these are the threads on the screw, and consider that we all know that Fleming's left hand rule and Faraday's laws of electromagnetic induction play a very important role under the working principle of DC machine. So here the corkscrew rule basically states that the direction of magnetic field, if I consider the direction of magnetic field like this, consider I am digging this screw into the wall now. So I am moving inside the wall. So my direction of magnetic field will be clockwise and the current will be inside or inwards. If I move the screw inside the wall, the direction of magnetic field is taken as clockwise and the current is inwards. If I move the screw in anti-clockwise direction, the current direction is outwards and this is anti-clockwise direction. So this is basically, corkscrew rule is basically used to denote the direction of magnetic flux produced by the current in the armature. So this corkscrew rule, so when the current is flowing inside the coil, the direction of magnetic flux can be taken as clockwise direction. When the current is flowing outside the coil, the direction of magnetic flux is taken as anti-clockwise direction. So this is the direction of flux. So this is basically given by corkscrew rule. So we can see in this figure, we have north pole and we have south pole. And you can see this is the armature. And these are the conductors. These are the conductors which are lying under the influence of north pole. And these are the conductors which are lying under the influence of south pole. So now when we consider under the north pole, the current direction into the plane is into the plane. So it is flowing inwards as determined by corkscrew rule. So we can see the clockwise rotation here, the clockwise direction of the magnetic flux. So we can see when the current is flowing inwards, the direction of rotation of magnetic flux is clockwise. So quite vice versa, when the current is flowing outwards under the influence of south pole, the current is flowing outwards and the direction of magnetic flux is anti-clockwise direction, which you can see here. So we can see the flux produced by the conductors under the north pole is downwards direction, and similarly the under south pole the current is flowing outwards of the plane, which you can see here, which is represented by dot. These conductors also produce the flux which is again directed downwards. So totally we can see that the armature conductors produce a flux through the armature in downward direction. So this is the direction of the armature flux under this particular case, that is case 2, when there is armature current and your field current is absent. Moving on to the next case. So in case 3, we can see that both field current and armature current, when both are present, when I have my armature current and field current in the picture, so what happens is we can see a distortion of the flux occurring here. So these two fluxes inside the machine, one is produced by the main field, as we know that, and the other is produced by the current in the armature conductors. So when these two fluxes combine together, we can see a resultant flux phi r which is produced in the machine. So this resultant flux phi r will be not along the polar axis, but it will be distorted like this from the either tips of the north pole and south pole. So we can see that for this north pole, this is the trailing tip and this is the leading tip. So we can see the flux here is high and we can see a less amount of flux here near the leading tip. And the same with the south pole. In the leading tip, the magnitude of the resultant flux is high, and in the trailing tip, the magnitude of the resultant flux is little low compared to the leading tip. So this is what we observed in case 3. So we can see that magnetic flux entering the armature is shifted and distorted. So this distortion in magnetic flux is due to the production of resultant flux, that is due to the impact of armature flux on the main field flux. So this impact of armature flux on the main field flux will cause the resultant flux to be distorted between the two poles. So we can also see that the magnetic neutral axis got shifted from its original position. So we can see that there is a displacement in the magnetic neutral axis, and this is a new magnetic neutral axis, the position of the new magnetic neutral axis. As I told you that the brushes also lie on the magnetic neutral axis, the brushes position will also get shifted to the new position. So the distortion increases the flux density in the upper pole tip of north pole and the lower pole tip of south pole. So we have seen that this distortion is thus increasing the resultant flux density on the upper pole tip and the lower pole tip of north and south poles. Similarly, there is decrease in the flux density on the lower pole tip of north pole and the upper pole tip of south pole, which can be seen here. On the either sides, we can see that there is a decrease in intensity of magnetic flux. Therefore, the direction of resultant flux has shifted the direction of rotation of generator. This is how, as the brushes rotate, when the magnetic neutral axis takes the new position, this also in turn changes the direction of rotation of the generator also. So since MNA is always perpendicular to the axis of resultant flux, hence MNA is also shifted. We can see that in the previous picture. Due to this nonlinear behavior and saturation of the core, the increase in flux in one pole tip is less than the decrease in the flux in other pole tip. So we have seen this. Here there is an increase in flux, here there is a decrease in flux. Here again there is increase in flux, and again we can see the decrease in flux here. So on the same poles we can find the different intensities of the resultant flux. both on the north pole and south pole. This results in the main flux. We can see that main field flux is decreased. Consequently, this main field flux will affect the generated EMF which is caused due to the resultant flux. So we can see that the main field flux gets decreased with the increase in load. So this gets decreased when we increase the load on the system. So these are the three cases of the armature reaction. So we can see that these are the different poles in the system. We can see that this is a leading pole tip, trailing pole tip, and the leading pole tip. So we can see the intensity of magnetic flux on either side on the different poles. So on the same pole, we find to the one side, that is to the trailing pole tip side, the intensity is high, and the leading pole tip side, the intensity is low. So that is the reason why this distortion or this decrease in the main field flux will cause the generated EMF also to be decreased. So this is the effect of armature reaction on the main field flux, thus decreasing the generated EMF in the generator. So now we have to see, we have seen that it causes different effects. So the effects of armature reaction now can be summarized like this. So armature reaction in the DC generator causes following adverse effects. The first effect is total field flux produced by each pole will be reduced. So this reduces the induced EMF in the generator. So we can see the first and foremost effect of the armature reaction is that total field flux will be reduced under each pole, so that the generated EMF EG also gets reduced. So due to the shifting of resultant flux on the MNA, we can see that the direction of rotation of generator is also getting changed. So this is also one of the adverse effects due to armature reaction. Due to the armature reaction, the first flux is established in commutating zone or the neutral zone. So this flux in the neutral zone induces again the conductor voltage, which causes commutation problems. So this is one of the adverse effect. We can see that due to the armature reaction, there is some amount of flux being generated in the commutating zone also. This commutating zone will again causes the voltage to be induced, and which causes problems in the commutation. So commutation process, we know that it is reversal of current or converting the AC quantities to DC quantities. So with this armature reaction, there is impact of this process of converting AC quantities to DC quantities also. So we have to find some mechanisms to reduce all these adverse effects on the armature reaction. So we have basically 4 methods to reduce the armature reaction problem. So the first one is we have to adjust the brush positions in the DC machine. So in this method, to rotate the brush mechanism, you have to rotate the brush mechanism to find out the correct neutral zone where both the cross magnetizing and demagnetizing effects which occur due to the armature reaction are neutralized. So basically this method is applicable to only fixed load currents. So only fixed load currents which require only fixed amount of currents without varying load currents. So this method of adjusting the brush position is only applicable to the fixed load currents. And then moving on to the modifying the ends of the poles. So in this method, the field pole tip is to be modified so that high flux cannot exist at one point, and at the other point we are seeing that there is a low intensity of flux. So in order to avoid that different intensities of flux which are being seen at the leading pole tip and the trailing pole tip of the field poles, so we have to adjust the field pole tips in such a way that high flux cannot exist on the ends because of the high reluctance part. So we have to make sure that there is a uniform distribution of the flux among the main field poles, such that there are no regions of high flux being concentrated only on the particular tips of the poles. So modifying the ends of the poles means we should ensure that there is a uniform distribution of flux without uneven intensity of flux being concentrated on the tips of the main poles. So other one is interpoles. Interpoles are the poles which are situated between the main poles. So main field poles. So by placing the set of interpoles or commutating poles, interpoles are also called as commutating poles, between the main poles of the generator, the polarity of the interpoles must be definitely be in the direction of main poles only, just next of it in the direction of rotation. So both the polarities of interpoles and the main field poles should be in one particular direction, that is in the direction of rotation. So interpoles are connected in series with the armature so that the respective fluxes rise and fall together with change in load current. So as the armature flux rises or fall with respect to the load, so these interpoles which are connected in between the main poles will neutralize the effect of this sudden rise and fall of the armature flux, such that there is no impact of armature flux on the main field flux. So these interpoles are kept to neutralize the armature reaction between the main field poles. Next one is compensating winding. So we provide one more type of winding. It is also known as auxiliary winding, which is embedded in the slots of main field poles. So we have seen that interpoles are situated between the main poles but connected in series with the armature conductors. So now we are seeing compensating windings, which is embedded in the slots of main field poles. So the compensating winding is connected in series with the armature in such a way that the direction of current in the compensating conductors in any one pole will be opposite to the direction of currents in the adjacent armature conductors. So we can see that there is in this way, the neutralization of, we know that in compensating winding, if there is any particular amount of current, it will set up its own armature flux. And we know that in the armature conductors, we have armature flux. So by placing these compensating windings, we can neutralize the effect of armature reaction such that this flux will neutralize the cross magnetizing and demagnetizing effect of the armature flux, such that there is no reduction in the main field flux, and thus there will be no reduction in the generated EMF by the generator also. So that is why we place one more technique called as compensating winding, which is one more auxiliary winding, which is embedded in the slots of main poles, so that it is connected in series with the armature in such a way that this current direction will be opposite to the direction of current through the armature conductors. Hence, compensating winding produces a flux which is equal and opposite to the armature flux, and thus it will neutralize the armature reaction. So these are the four methods to neutralize the armature reaction effect. That is nothing but adjusting the brush position, which is applicable to fixed load currents, and we also modify the end of poles such that there is a uniform distribution of flux. We place interpoles in between the main poles which are connected in series with the armature windings, such that these interpoles will align with the main field flux, but they will neutralize the armature reaction produced by the armature conductors. So it will neutralize the sudden flux rise and fall due to the sudden load changes in the armature conductors. And then next one is the compensating winding. It is the auxiliary winding which is placed in the main poles. So this main poles, it will produce a flux which will neutralize the effect of armature flux, thus neutralizing the armature reaction effect and thus increasing the field flux in the generator. So now we will be seeing about the demagnetizing ampere turns and the cross magnetizing ampere turns as a part of armature reaction. So we can see that here we have north pole and south pole, and this is your armature which is embedded in between the north and south poles. We can see the different conductors here. So if I assume the demagnetizing ampere turns are neutralized by adding the extra ampere turns to the main field windings. So it is essential to calculate their particular number, how many number of demagnetizing ampere turns are required to neutralize this demagnetizing effect which is caused due to the armature flux. So before proceeding, it should be remembered that number of turns will be equals to the half number of conductors. So if Z is the number of conductors. So number of turns will be half of the number of conductors. So one turn will be half of the number of conductors, or one conductor is equals to 2 turns. So this can be remembered as a part of this. As 2 conductors constitute 1 turn, so next moving on to demagnetizing ampere turns per pole. So looking at this figure, we see we have a north pole and we have a south pole, and the direction of rotation. This is your MNA. So we have to now calculate the number of demagnetizing turns which are required, ampere turns which are required to neutralize the demagnetizing effect in the DC generator. So to calculate that particular number, so we have to see that number of turns is equals to the half number of conductors. So because 2 conductors, that is, constitute 1 turn, we can see that here coil side 1 and coil side 2. So they constitute 1 turn, 1 complete turn. So 2 conductors constitute 1 turn here. So Z is the total number of conductors, armature conductors. I is the current which is flowing in the each armature conductors. So we know that for wave winding, the parallel paths is equals to 2. Always it is equals to 2. Next, we are going to calculate about the demagnetizing ampere turns and the cross magnetizing ampere turns which are required to neutralize this armature reaction in the DC generator. So first we are seeing about the demagnetizing ampere turns. For this, we consider an armature which is embedded between the north and south poles of a DC machine. We know that one complete turn in a conductor in an armature will require 2 conductors. This is coil side 1, this is coil side 2, or this is conductor 1 and the conductor 2. So we should remember that the number of turns is always equals to half the number of conductors. So if we consider there are Z number of conductors in the armature, in which I is the amount of current flowing in each armature conductor. So for wave winding, we know that the parallel paths is equals to 2, and for lap winding, we know that the number of parallel paths is equals to the number of poles. So we can see that for simplex wave winding, the current is nothing but, current in each parallel path is nothing but IA by 2, and for simplex lap winding, it is nothing but IA by P. So, and theta M is the forward lead or the displacement of the MNA from the original MNA in geometrical or angular degrees. So if I consider theta M as the displacement in MNA, total number of conductors in angles, that is nothing but in this particular region, is nothing but demagnetizing ampere turns. So we can see that in the region AOC and BOD, in this particular region AOC and BOD, we see that under the influence of 2 poles on the in angle AOC or in this region AOC and BOD. In AOC, it is nothing but 2 theta M by 360 into Z, and again the same thing on the below side. So it is multiplied by 2. So together it is 4 theta M by 360 into the number of conductors. As 2 conductors constitute 1 turn, so we can see that this can be further, total number of turns in these angles will be equals to, we have seen with respect to conductors as 4 theta M by 360 into Z, and if we calculate it with respect to the number of turns in these angles, so we get Z divided by 2. So this complete equation will become now as 2 theta M by 360 into Z into I. If we consider it for wave winding, we can see that it is into I by 2, which gives the equation 2 theta M by 360 into Z into I. So the demagnetizing ampere turns, if we calculate it per pair of poles, we get it like this, that is 2 theta M by 360 into Z into I. And this demagnetizing ampere turns, if we calculate it per one pole, then again this equation will be divided by 2 and we get it theta m by 360 into Z into I. This is the ampere turns per pole, or the demagnetizing ampere turns per pole. It is a formula to calculate, so that by calculating this demagnetizing ampere turns per pole, we neutralize the armature reaction, or we calculate the number of ampere turns required to neutralize the demagnetizing effect in armature reaction. Moving on to the cross magnetizing effect. So now if we observe the conductors which lie in the regions AOD and BOC, which are responsible for the cross magnetizing effect in the DC generator, known as distorting conductors or the cross magnetizing conductors. So these are responsible for the distortion of main field flux or the resultant flux which is caused due to the armature flux and the main field flux. So we see that total number of conductors per pole in both cross magnetizing and demagnetizing effects are Z by P. So if we consider Z as the number of conductors, P as number of parallel paths, we see that total armature conductors per pole can be written as Z by P. Demagnetizing conductors per pole, we have already calculated it as 2 theta m by 360 into Z, as we have seen in the previous slide. So cross magnetizing conductors per pole will now be total conductors per pole for both the cross magnetizing and demagnetizing effect minus the conductors which are required for the demagnetizing effect will give you the cross magnetizing conductors per pole. So from this we can get the equation for a cross magnetizing conductors per pole as, when we take I as common, we see that this is Z into I. So Z into I. So if we take I common, we get here as these are the number of conductors. If we take ampere conductors, we multiply this particular equation. We multiply this particular equation with I. And cross magnetizing ampere turns per pole, if we take it as, again we divide this equation by 2. This is per pair of poles and this is per pole. If we calculate it per pole, you get the final equation as Zi into 1 by 2p minus theta m by 360. So remembering that two conductors make one turn, your equation will be the number of cross magnetizing ampere turns required to neutralize the cross magnetizing effect which is occurring in armature reaction is given by this equation. So to calculate the demagnetizing ampere turns and the cross magnetizing ampere turns, how many number of compensating windings to be placed or how many number of interpoles to be placed can be given by this demagnetizing and cross magnetizing effects. This is about armature reaction. So we have seen here today, coming to the summary of today's lecture, we have seen that what is armature reaction, and we have analyzed the three cases of the armature reaction: under no load, and when we only have armature current, and when we have both armature current and field current, and how the distortion of flux has occurred in this particular case, and what are the adverse effects of armature reaction. We have also seen what are the methods to neutralize the armature reaction. We have also calculated the demagnetizing ampere turns and the cross magnetizing ampere turns required to neutralize the armature reaction in DC generator. This is about armature reaction. Thank you.